Welcome to this particular module, and this is a part of next lecture which is focused on what is a clean room and why the clean room is required for tissue culture and what a class of the clean room. Along with that, we will also see what should be or what are the possible equipment that one can have in the laboratory to run experiments related to bioengineering. When I am talking about bioengineering, that is the combination of engineering, combination of biology, combination of some of the chemistry as well, or you can say biochemistry as well, right. So, let us see in next few minutes what exactly clean room means, right, and then we will continue this module as a part of lab experiment, where I will actually show what are the equipment within a clean room, right. So, if you see the slide, what you see is that the tissue culture, what we have learned until now, cell and tissue culture. So, the cell and tissue culture room needs to be preferably housed in a clean room environment. A typical clean room looks as shown in figure aside. You look at this figure and see what exactly you can see in this particular figure. So, if you see, this is a clean room that you can see, and the personnel within the clean room, they are wearing the clean room gown. This is to avoid any contamination within the clean room. Now, when you talk about clean room, what exactly clean room means? Clean rooms are classified based on the amount of particulate matter contained within the targeted space, right. So, how many particulate matter is there within a given targeted space? Based on that, we can classify the clean rooms, and there is a ISO classification already there, as well as FED classification, which is listed below, and you can see there is a class ISO 1 to ISO 9, and within the class ISO 1 to ISO 9, you can see what kind of maximum particles per cubic meter should be there for the clean room to be classified as class ISO 1. Let us talk about class ISO 1. You can see 0.1 micron or greater, only 10 particles per meter cube, while 0.2 is about 2.37, greater than 0.3 should be 1.02, greater than 0.5 would be 0.35, 1 micron can be 0.083, and greater than 5 micron would be 0.0029. With this stringent classification or the amount of particulate matter, you can say that this is classified as ISO 1. Generally, what you see is ISO 10 kind of ISO 4 kind of clean room, where it is class 10 FED STD 209 E equivalent, where you see that ISO 4 there can be 10,000 particulate matters or maximum particles per cubic meter when we are talking about 0.1 microns, while when we are talking about 5 microns it should be 2.9 particles per cubic meter when you want to classify the clean room as class 10. Okay. So, this is very important point that you need to understand. Same way, when we talk about our laboratory environment is somewhere around ISO 9, but if I will if the laboratory has a positive pressure module, which we will see in the following slides, and I will show you actual positive pressure modules with HEPA filters in my laboratory, that we can bring the class down to class 10,000. Now, the one that you see right in the screen is the class 1000 kind of clean room, and the clean room classification also depends on something called HEPA filter. HEPA, HEPA stands for high energy particulate air, and filter is a filter. So, HEPA filter, the number of HEPA filters you install in a clean room and how many times you are circulating the air. So, circulation per minute, right, that defines or that helps to maintain the class of the clean room. So, there is a conventional clean room when the HEPA filters are used on the along with the clean room in the clean room facility, where when we talk about non-conventional class of clean room, then you will see the laboratory which we will show you as a part of this course, where there are there are positive pressure modules, and the positive pressure modules are connected with HEPA filters, and we require an air conditioning unit to circulate the air and keep the environment constant. That means that we require the temperature to be at 27 degrees centigrade, we require the RH to be let us say 45 or 50, whatever we want to have in a controlled environment. If we perform experiments in a controlled environment, the repeatability, the accuracy would be higher. I have told you to look at repeatability, accuracy, resolution. So, now you should have the understanding what exactly the difference between all three of those terms are. If you talk about Intel Fab 32. So, Intel Fab 32 is rated as class 10 clean room, meaning there are no more than 10 particles measuring 0.5 micron and or larger per 1 cubic foot of air, while the laboratory, that is my laboratory, is a class 10,000 clean room, right. That is what we have discussed, and this is how the ISO classes are there. Now, the requirement for the cell culture, for the tissue culture, if you do the tissue culture in a preferably housed or if the tissue culture is housed in a preferably clean room environment, then the contamination would be sufficiently or substantially low compared to when it is not kept in a clean room environment. So, that is the reason of having a clean room. When you generally see a clean room conventional kind of facility 1000, 10,000 or 100, you will see that there are several equipment placed within that facility, and those equipment are a few of those equipment are shown here. If you see from the left one, the top left one is the LP-CVD furnace, or you can say it LP stands for low pressure, CVD is chemical vapor deposition furnace. Okay. So, this kind of furnace can be used to grow thermal silicon dioxide. The process is also called thermal oxidation, and the temperature that is used for growing silicon dioxide would be close to 1100 degrees centigrade. Again, within the oxidation there are two types of oxidation, there is a dry oxidation, there is a wet oxidation. So, we will see if the time permits, because our focus is more on developing the electronic system for cancer diagnosis. However, when you are talking about developing a system, the system would consist at some point some microchips or microsensors, and those microsensors we can fabricate with the help of equipment shown here and in the clean room facility. The next one is a PECVD, and PECVD stands for plasma enhanced chemical vapor deposition. This is used to grow silicon dioxide and silicon nitride, but the advantage of PECVD over LP-CVD is that the temperature used for the reaction is very low. When you say very low compared to LP-CVD, temperature is about 400 degrees centigrade, and in LP-CVD I was talking about 1400 degrees centigrade. Now, why then PECVD we have to use if the LP-CVD can be sufficiently good for us to grow oxides? Why low temperature is required? So, I will give you a quick example. If you have a aluminum layer, let us say my mobile is an aluminum layer, and my hand is a silicon substrate, and on this I want to grow another oxide. So, like this is a sandwich, right, silicon, aluminum, silicon dioxide, right. So, if you see, this is silicon, this is this one is your metal which is aluminum, and this one is silicon dioxide. When I want to grow silicon dioxide on metal, on this metal, my temperature, if it is 1100 degrees centigrade, the melting point of aluminum is extremely low. So, it will melt when you are growing silicon dioxide onto the aluminum. But if we can grow silicon dioxide on aluminum at 100 degrees centigrade, 100 degree, 200 degrees centigrade, then there is no issue of melting of aluminum. That is the advantage of plasma enhanced chemical vapor deposition over LP-CVD. However, every time if there is a system which has some positive points, there are some limitations as well. So, what are the limitations of PECVD over chemical vapor deposition, which is LP-CVD? This is also chemical vapor deposition, it is just plasma enhanced, that is a low pressure. So, the thermal oxidation gives a better quality of film compared to PECVD. So, if you require a film quality to be extremely good, then you have to rely on thermal oxidation. For devices such as the micro electromechanical systems based sensors, you can use LP-CVD as a intermediate layer or as a insulating layer between two metals, okay, or metal and a semiconductor. So, I will talk about that at some point. Then you see is a CVD system which is from tester equipment. Next one is the chemical mechanical polisher. This CMP machine is used to polish the wafer. So, generally I will show you the silicon wafer in next few classes, and you will see that there are two types of silicon wafer when you talk about from the roughness point of view, one or polishing point of view. One is single sided polished wafer and one is double sided polished wafer. On a polished wafer which is single sided, and if the second side is rough, if I want to polish it and to make it as smooth as this the front side, I had to use chemical mechanical polisher. And like I said, once I show you the silicon wafer, you will understand more about how the CMP machine can be used. Next one you can see is a dicing saw. Once you have a wafer with chips, how can you dice it up? So, let me give an example. If you can see here, right now in my hand is a keyboard. Can you see? Yeah, this is a keyboard, right. Assume that this is a silicon on which there are multiple chips. I want to slice each of the chip. How can I slice it? So, I had to rely on a machine which is called dicing saw micro actuation or micro automation, where it will slice it individual chips in the dimensions or in the with the precision that I want. So, from one chip to second chip, I can monitor it. I can put the values into the system, so that it will cut the chip without harming the next chip next to it. Okay. So, dicing saw is something very important equipment when you are talking about microchips that you need to cut out of the wafer. However, if you consider this as a silicon wafer, there is you can use a diamond cutter. It is like a pen with a diamond tip, and you can, if you just scratch it off like this, that and you press it, then what will happen? It will break into piece. So, there are like, but that is not a good way of cutting off the chip from the silicon wafer. So, we have to rely on a standard method, which is your silicon or saw dicer. Okay. So, that is what you can see saw dicer in the slide. Next one is the EVG 501 bonder. Can you see in the slide? EVG 501 bonder. So, that one is used to bond silicon to silicon. EVG bonder, silicon to silicon, two silicon wafers when we want to bond, we can use a EVG bonder. Next one you see is a metathermal evaporator. So, metathermal evaporator is used to evaporate the metal onto the and to deposit a thin film of a metal onto the substrate. We will discuss more about thermal evaporation in the lectures. Next one we have is a parylene deposition system. Parylene deposition system is used to deposit polymer on the substrate, on the silicon. So, parylene is like a thin plastic. So, if you want to grow have a parylene layer on the substrate, silicon substrate or oxidized silicon substrate, then you can use the parylene deposition system. Next one we have is a AJA sputtering unit, and sputtering is another phenomenon by which is a part of physical vapor deposition, where we can sputter the metal and we can deposit the metal on the substrate. We will see again most of this equipment is a part of the lecture notes in the future. We will see next one what we see is an E-beam evaporator. It is an electron beam evaporator, again to use the metal using the E-beam technique. The advantage of E-beam, or why we have to go for E-beam over thermal evaporator, is that in the E-beam you can deposit a metal which is having a high melting point, while thermal evaporator has a drawback that the melting point of the metal is not too high, you cannot thermally evaporate it. We will discuss what exactly that means when we discuss about thermal evaporator. Next one is your Denton E-beam thermal evaporator, followed by photoresist spin station. So, when you will look at the photolithography, you will understand what is important of photoresist spin station as well as the EVG mask aligner. If you see Headway EC101, next one is photoresist from Laurel, next one is spin station, but next one is the EVG 620 mask aligner. Followed by you have MJB 3 mask dual side mask aligner. There is a single side mask aligning, dual side mask aligning, we will discuss in detail. Next is when we had to bond PDMS. PDMS is a silicon, SiLiCone, and to that if you want to bond a glass, then we have to do a oxygen plasma. How can we do oxygen plasma? We can do oxygen plasma with the help of Mars Jupiter 3O2. This is one of the equipment. There are many equipment available in market. This is one system where you can show that we can do oxygen plasma system. Then when we want to etch a metal or a semiconductor or a silicon, we can use wet etching bench. We have next one is RIE, which is a hard or dry etching chlorine and dry etching fluorine. Finally, we have a deep RIE, which is deep reactive ion etcher, and that is for etching silicon, but the deep reactive ion etching is much faster compared to reactive ion etching system. So as you see, there are so many equipment within a conventional clean room, whether it is 100, 1000 or 10,000, and as a part of this course we will go through most of the equipment quickly, so that you understand that how it can be used to fabricate the sensors. Once you fabricate the sensors, then we have to develop a system in which the sensor can be placed. You have a mechanical zig or you have a press fit contacts instead of soldering or wire bonding, because soldering and wire bonding will cause damage sometimes, and it is difficult to replace the chip. So can we come up with a different technology where we just use a press fit contact to the chip, and every time we do not want the chip, we can just remove the contact, we can throw the chip, load another chip. So that is about the mechanical design along with the electronic chip, but how an entire system will look like, that is our idea, and how it can be used for diagnosing cancer. So we will look at that particular things. Now if we just talk about how a lab has to or should have different equipment when you want to work at the interface of engineering and biology, engineering and medicine, engineering and chemistry. So if you look here in the slide, what I am going to show you is equipment from left to right. The first one on the top left is your thermal evaporator, followed by pathology workstation. Then we have 3D cell culture, we have BSL2, which is biosafety hood 2, we have cell imaging microscope, and then we have spin coater, which is then we have peristaltic pump, the one that you can see on the next line. Peristaltic pump is with the wires, right, with the wires over here, and then we have the upright microscope, followed by fume hood, which is a bio base you are written here, which is a fume hood. Then we have micro manipulator, we had discussed micro manipulator in the last module, and then we have a CO2 incubator, which we have discussed. We have O1, we should have a DI water plant, and we have a oxygen plasma system. So these are the system or equipment which are basic equipment that one should have, or if it is there in the lab, it is easier for a person to work at the interface of biology, medicine and engineering. We here are looking at another set of equipment. The top left, you have to go from top left. The first one is wet bench, which is solvent. Acid bench and solvent bench are different, followed by a mask aligner. Then we have towers with HEPA filters. Like I said, these towers can be placed into the laboratory to bring the environment down to class 10,000, depending how many towers we are bringing in, and these are high energy particulate air filters, which are HEPA filters installed into these towers. Followed by we have a vacuum oven, then we have wet bench, we have high resolution quantitative phase microscope, we have autoclave, and we have a microtome. We have discussed most of the things. However, the one that we have not discussed, we will discuss in the following lectures. Okay. So these are the equipment that will help researcher to work at the interface of bioengineering. Now when we talk about why these kind of facilities are important, or is clean room really important, that should be a question, right. So yes, when we see the top universities in the world, including Israel, we have Fuji Electric, we have Berkeley, and we have Stanford, we have Brick Neanderthal Center at Purdue. They have a dedicated whole a center for performing or to facilitate bio nanotechnology as well as MEMS based bio-MEMS based devices, microfluidic systems, medical diagnostics, genomics, proteomics, cell biology, you know. So we require this kind of center or a clean room environment, and with that particular purpose here at IISc we have a center for nanoscience is a sense and engineering which is right in the campus. It has all the facilities and most of the equipment that we are talking about as a part of the center facility for the IISc student. They also have a very beautiful program called INUP program, through which people from other part of our country can come and can learn, as well as it is a free training program. So as far as I know, you have to go through the department website and understand more about those things. But when you are talking about engineering and biology, I will show you how the lab that we have right over here in the Department of Electronic Systems Engineering at Indian Institute of Science looks like, and what exactly equipment are there and how it will help us to work on this interface. Right. So, with this approach our institute also have started working towards this kind of facility where we are talking about bioengineering, we are talking about interdisciplinary research, and whatever I am teaching today or the part of this whole course is a interdisciplinary research. So, how to use your engineering knowledge to come up with a novel solution regarding to medicine or biology. Right. Now, let us see one more slide talking about HEPA filters, and we will end our lecture or this particular module right over here, and then in the following lectures we will talk about other topics. So, if you talk about just a HEPA filter, you can see here on the slide that the critical particulate concentration is controlled and maintained in a clean room environment using HEPA filters. Like I said, HEPA stands for high energy particulate air. A representative air cleaning setup using HEPA filter is shown here. You can show this particular system, right, where there is a coarse filter, there is a rotary air heat exchanger, there is a electrostatic cleaner, there is a HEPA filter, and there is a fresh air, there is a exhaust air. So, this is the circulation of the air. And if you talk about positive pressure modules and our modules, it looks like this. We will actually see these modules in the lab class. It is usually consisting of positive pressure module that cleans the incoming air through an array of filters you can see here, and pushes the air into the room, maintain it at a higher pressure so that particles do not enter easily. Along with the positive pressure module, there will be also a tower modules for circulating the internal air, and finally the HEPA filter system forms the core mechanism through which the clean room environment is maintained. Right. So, it is an extremely important component for any clean room laboratory. Right. This is the last slide for me for this particular module. So, we will discuss more about other modules in my next class. Till then you just go through this lecture notes. This is more like a information, and we will see how can we actually interface our engineering knowledge, which requires really basic engineering, but with the idea of how to use these devices or that engineering knowledge to form an entire system. Right. Not always you require a top level of understanding or knowledge to develop a system. You require a right approach, you require understanding about one particular subject in detail. Right. And then along with your friends, along with the colleagues, along with the persons who are expert in their own field, you have to start collaborating. That collaboration will give you an actual thing to work. Right. So, how we will use, so we will see a 3D printer as a part of this course, right. Haven't I said that? I said that. Why 3D printer? For how it is related to electronics engineering? It is not, but 3D printer is used for making the mechanical casing, and it is used exclusively. So, it is good to know how 3D printer will work. Right. That is the idea. The idea is not to just learn a specific subject, but also to understand what other subjects or what part from other subjects can be used to develop an entire system. Of course, you require a thorough knowledge when you develop an entire system, but what I am saying is that with the prerequisites of basic electronics, you will see and you will learn how to use it to for solving a particular problem in a medical domain. Right. Till then you just take care, and I will see you in the next class.